As we gazed up at the heavens, we asked where we had come from, how all the stars were created, how all the elements were made, even how the universe itself had begun. One of mankind's greatest achievements is that we've answered these questions. What is truly remarkable is that this understanding has come through the study of the smallest building blocks of matter, atoms. As we peered inwards, we realized we could explain what we saw when we peered outwards. The atom has helped us solve the greatest mysteries of existence.
Everything in the world we see is made out of tiny objects called atoms. And yet we only proved their existence at the beginning of the 20th century. The first shock was to discover how small they were, less than a millionth of a millimeter across. There are trillions in a single grain of sand.
Amazingly, we now have a pretty good idea of the number of atoms in the known universe. Now, given the vastness of the universe and the minuteness of the atom, it's not surprising that this is a mind-numbingly huge number. It's 1 followed by over 70 zeros. That's a trillion, 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 trillion atoms. We don't only know the raw number of atoms in the cosmos, we also know that they come in 92 different flavors. These are called the elements, and you'll recognize many of them as familiar parts of the world around us. Oxygen, iron, carbon, tin, gold, and so on.
Everything in the universe, the stars, the planets, the mountains, the seas, the animals, you and me, we're all made of these atoms, or combinations of them.
It's an astonishing human achievement that we now know not only how many atoms there are in the universe and how many different types there are, but why they exist at all. We can now explain how every one of those trillion, 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 trillion atoms was created. It turns out that the answer to the mystery of creation itself lies within the heart of each and every atom in the universe.
The story of how we came to understand creation itself started over 100 years ago in a small laboratory in southeast Paris. This piece of paper is a remarkable artifact. It's from the notebook of the woman who first studied radioactivity, the chemist Marie Curie.
It's incredible, 100 years later, and this piece of paper is still spitting out radioactive particles.
Still stuck to the paper are tiny but intensely radioactive particles of a substance that Marie Curie discovered in 1898, a substance she called radium. It was a sensational discovery for one primary reason. Though radium looks like an unremarkable grey metal, it contradicted all the then known laws of science. Because radium pumps out invisible yet powerful rays of energy which could fog sealed photographic paper and burn human flesh. Also, radium appeared to contain within it an inexhaustible store of energy. Curie worked out that a gram of radium, a piece much smaller than a penny, contains more energy than 100 tons of coal. To the scientific community, radioactivity was just about the most exciting thing possible. The brightest minds of a generation clamored to study it. And the price of radium, its most potent source, soared to thousands of pounds per ounce. And radioactivity didn't disappoint. In 1919, it produced its greatest revelation yet. a revelation that would ultimately lead to a fundamental understanding of the atomic world. The revelation was that radioactivity allowed humanity to fulfill an age-old dream: to become alchemists.
Alchemy, the power to change base metals into gold, the quest for the so-called philosopher's stone, which has the magical ability to transmute one substance into another, has been an obsession for centuries. It conjures up wonderful tales of sorcery and wizardry, as anyone who's read Harry Potter knows very well. The power and wealth that would surely come to anyone who mastered alchemy seduced many great scientists and thinkers, like Isaac Newton, Robert Boyle, and John Locke. All of them tried to change one element into another, and all of them failed.
Then, in 1919, the secret of alchemy, the mystery of the philosopher's stone, was finally revealed, not in a wizard's den, but in the physics department at Manchester University. The world's first true alchemist was Ernest Rutherford. A loud, straight-talking New Zealander, Rutherford had come to dominate the study of radioactivity. He had wonderful intuition and was fearlessly prepared to challenge conventional wisdom. And alchemy would require Ernest Rutherford to follow his intuition deep into the unknown.
The discovery was almost accidental. It began when one of Rutherford's students noticed that when radioactive materials like radium were placed inside a sealed container of ordinary air, mysteriously, small amounts of the gas hydrogen begin to appear. Now, this was bizarre. Ordinary air contains virtually no hydrogen, and yet, in the presence of radioactivity, it was appearing out of nowhere. This was precisely the kind of problem that Rutherford, now at the height of his powers as an experimental physicist, loved, and he flung himself at it. He began by isolating all the different gases that make up the air we breathe: nitrogen, oxygen, water vapor, and carbon dioxide, and studied how each of them behaved in the presence of radioactivity. And then, eureka! Rutherford realized that in the presence of powerful radioactive rays, the gas nitrogen, which makes up about 80% of the air we breathe, changes into two new substances, the gases oxygen and hydrogen. Then and there, Rutherford had transmuted one element into two others. He'd become an alchemist, and radium, with its powerful radioactivity, was the philosopher's stone.
The press hailed Rutherford as the first alchemist, but in fact that was the least of it. What alchemy had shown him was the inside, not just of the atom, but of the strange object at its center, its tiny beating heart, the nucleus. To get a sense of this achievement, remember Rutherford and his contemporaries at Cambridge had only a sketchy idea of what an atom was, but they did have an idea of its size.
And it's mind-numbingly tiny, 1/10 of a millionth of a millimeter across. Let me put it another way. There are more atoms in a single glass of water than there are glasses of water in all the oceans of the world.
And Rutherford now also knew that the atom had structure, that within the atom there was a subatomic world. He pictured each atom like a tiny solar system. At its center was an object which Rutherford called the nucleus. Orbiting this, like planets, were the electrons. But what on earth was the nucleus? Rutherford was convinced that alchemy had shown him the answer.
To understand how Rutherford did this, we have to get inside his head, to think like he did. Rutherford had fantastic intuition, coupled with an intensely practical approach to science. So he hated ideas that relied on complicated mathematics. When it came to the atomic nucleus, Rutherford looked for the simplest idea that worked. And what worked was to imagine that the nucleus is made of tiny, rigid spheres, like snooker balls. Using this incredibly simple image, Rutherford could construct all the elements in the universe. He could explain how the huge variety of different atoms are made of the same basic components. So here's how it works. Hydrogen, which is the simplest element, consists of just one sphere, which Rutherford called a proton, which is the Greek word for first. All the other elements are made by adding more protons to the nucleus. It's as simple as that. So helium, which is the second lightest element, comprises of 2 protons. Lithium has 3. Carbon, which is the element that's the basis of all life, has 6 protons. The oxygen that we breathe has 8. And uranium, which is the heaviest naturally occurring element, has 92 protons. This was Rutherford's inspirational idea, that each element is defined by the number of protons in its nucleus. It's a wonderfully elegant and simple idea, an idea that explains how so much of the universe we see around us is constructed.
But as scientists often find, nature is never quite as simple as it seems at first sight. Sure enough, a big problem emerged with Rutherford's proton. And it was to be one of Rutherford's own protégés who was the first to identify it.
Francis Aston was an interesting character. As a young man, he enjoyed the adventurous outdoors and was into skiing and motor racing. And apparently in about 1909, he discovered surfing off Waikiki Beach in Hawaii. But he soon realized that the call of the physics laboratory was greater than the call of the waves. And it was while at Cambridge that he invented an incredible piece of equipment. That's now housed here in this rather austere and plain-looking building, the Cavendish Laboratory. This is Aston's original spectrograph. It's an amazing piece of equipment because with it, for the first time, scientists were able to weigh individual atoms. It's incredible. It looks a bit like a gun. It's a very strange shape.
Now they could weigh atoms accurately. They discovered that there was a fundamental problem with Rutherford's model of the nucleus.
Basically, the numbers didn't quite add up. All the atoms of the known elements, apart from hydrogen, were much heavier than they should be. For instance, helium with 2 protons should weigh twice as much as hydrogen with just 1. In fact, it's 4 times as heavy. Rutherford realized this could mean just one thing. Apart from the proton, there's something else inside the atomic nucleus. But what?
It took 12 years to find the answer. Now, as head of the prestigious Cavendish Laboratory in Cambridge, Rutherford threw all his resources into the project. He bullied and cajoled his students and researchers until one, called James Chadwick, hit the nuclear physics equivalent of gold.
Chadwick built this in 1932, and to think that with just this tiny little piece of equipment, he discovered the missing ingredients of the atom. For me, as a practicing nuclear physicist, this really is an amazing device. When I think of the huge accelerators that are built today to conduct experiments to probe the nucleus of the atom, it's really awe-inspiring in its simplicity, really.
He put a source of radioactivity at this end of the tube, and the radioactivity then struck a small target in the middle here. And then out of the target came new particles that sprayed out of this end here. It's a bit like an atomic gun shooting out Rutherford's missing particles.
What Chadwick discovered was that along with the proton, there's another kind of particle inside the nucleus. It weighs almost exactly the same as a proton, but is much more elusive because it carries no electrical charge. Technically, we say it's electrically neutral, hence its name, the neutron. And it immediately solved the problem of the weight of atoms. So helium is 4 times as heavy as hydrogen because, along with its 2 protons, it contains 2 neutrons. And oxygen has 8 neutrons along with its 8 protons, making it 16 times as heavy as hydrogen. So in 1932, the atomic family was complete. Scientists announced that every atom in the universe is made of just 3 basic components: electrons, tiny particles orbiting a nucleus, which in turn is made of protons and neutrons.
Over Christmas 1932, physicists at the other great centre of atomic physics, the Niels Bohr Institute in Copenhagen, celebrated the neutron's discovery and the completion of the nuclear trinity by writing a musical about it.
That which experiment has found, for theory had no part in, is always reckoned more than sound, to put your mind and heart in. Good luck, you heavyweight ersatz, we welcome you with pleasure. But passion ever spins our plot, and Gretchen is my treasure.
Some of the great names in physics took part in this musical. Their excitement was primarily due to one thing. They knew they stood at the threshold of an entirely new kind of science with entirely new rules, what we now call nuclear physics. The first challenge for nuclear physics was this. Although physicists now knew what the tiny nucleus was made of, they couldn't explain how it all held together. In fact, it was worse than that. The existing laws of physics predicted that every atomic nucleus should self-destruct instantly.
Neutrality pulls us along.
The main problem was this. All protons, the key ingredient of the atomic nucleus, have positive electric charge, and things with the same charge repel each other, just like these magnets. Look. So, just like these magnets, if 2 protons get close together, they should then just fly apart. But weirdly, inside the atomic nucleus, they don't. Dozens of protons can stick together alongside each other. So what sticks them together? What stops the protons from flying apart? The answer was big news. It was nothing less than an entirely new force of nature. For centuries, humans had only ever encountered 2 natural forces: gravity, which pulls us down to the Earth, and electromagnetism. But now, hidden inside the atomic nucleus was something completely new. It was called the strong nuclear force. And the easiest way to imagine it is with some Velcro.
If I put Velcro around these magnets, they start to behave slightly differently. At first, they repel each other just as before. But when they get close enough, the Velcro kicks in and they stick.
The effect is very short range, but very, very strong. And it's exactly the same with protons. The strong nuclear force explains what holds the nucleus together.
The strong nuclear force works between all protons and neutrons. But what is truly surprising about it is its strength. It's by far the most powerful force in the universe. More than 1 trillion times stronger than gravity.
Think about it this way. If I was pulled down to the Earth, not by gravity, but by the strong nuclear force, then I'd weigh trillions of times more than I actually do. In fact, I'd weigh more than the entire galaxy. But the reason I don't weigh that much is because the strong nuclear force is only felt down at a distance of a trillionth of a millimetre. With the strong nuclear force, humans finally began to get a glimpse of what was actually going on inside the atomic nucleus. Roughly speaking, all nuclear behaviour is down to a balance between the strong nuclear force squashing the protons and neutrons together and the electric charge on the protons forcing them apart.
Physicists realised that picturing the nucleus as a battlefield between different elemental forces solved one of the oldest mysteries of all time.
It's this, a question that humans have asked ever since the dawn of time, is how does the sun shine? Now, sunlight is the source of all life on Earth, but how is it made? It's all to do with the forces inside the atoms that make up most of the sun. Hydrogen. This is how it works. The nucleus of a single atom of hydrogen consists of just a proton. And every now and again, inside the high pressure, high temperature cauldron of the sun, this proton can get squeezed up close to another and bang, the strong nuclear force kicks in and fuses them together. Now, this is a process that eventually leads to the creation of a helium atom, and it's accompanied by the release of energy as a burst of light and heat. It's a bit like slamming two cymbals together and releasing a burst of sound. Hydrogen fusing into helium, and the energy released is what we see and feel as sunshine.
This process of two hydrogen nuclei slamming together and releasing energy became known as nuclear fusion. The turmoil between the strong nuclear and electromagnetic forces as they strive to dominate the nucleus does more than just power the sun. It's at the heart of everything. But in the late 1930s, before people figured out that story, nuclear physics did something much closer to home. In no uncertain terms, it redefined the history of mankind right here on Earth.
The atom bomb changed everything. The excitement of pre-war scientific research, the days when physicists sang songs about their discoveries, were over. Robert Oppenheimer summed up the grim mood with these words: "The physicists have known sin, and this is a knowledge which they cannot lose."
The terrible irony of the atomic bomb is that because of the scientists' sin, because of that knowledge that cannot be lost, something of great significance did emerge. Something that would ultimately reveal the full story of the 14 billion years of the entire universe. The war had caused a massive $2 billion to be poured into nuclear research. People now knew an astonishing amount about the atom and its nucleus. Specifically, scientists had detailed measurements of how stable or unstable different atomic nuclei were. That stability was a direct result of the battle between the strong nuclear force holding the nucleus together and the electromagnetic force pushing it apart. In some atoms, the balance tipped towards the strong force, making them very stable. But when the electromagnetic force had the upper hand, they were inherently unstable. By the late 40s, scientists began to investigate the implications of the way nuclear stability of atoms varies. They noticed one very strange fact about the nuclear stability of one particular atom. Of all the 92 different elements, of the 92 different types of atoms that make up the universe around us, gases like hydrogen and oxygen, solids like carbon and silicon, metals like gold and silver, one is special: iron. So what makes iron so special? It stems from the unique structure of its nucleus. The 26 protons, along with the neutrons, combine in a very special way to make iron incredibly stable. For some reason, nature has decreed this as the number that allows the strong force and the electromagnetic force to balance each other perfectly. It makes iron the most stable element in the universe. Now we can understand why fusion occurs. Lighter atoms can combine together to become more iron-like. And fission is the opposite process. Atoms heavier than iron can split apart into lighter, more iron-like pieces. So all elements seek the stability of iron. And that fact underpins the whole history of the cosmos. The best way to understand this is to imagine the relative stability of atoms as a couple of graphs.
Here's what they show. The very lightest elements, hydrogen and helium, are not quite as stable as they could be. They'd like to be something else, something even more stable. Similarly, the heaviest elements like uranium and polonium are actually unstable. In fact, they're so unstable that they fall to pieces naturally through radioactivity. And here in the middle are the most stable atoms of all: nickel, cobalt and iron. So far so good. Now here's the amazing bit. This nuclear stability graph turned out to be uncannily similar to a different graph altogether. But it was a similarity that no one had ever suspected. That's because data from this other graph came not from the tiny nucleus, but from as different an arena as you can imagine: the vast expanses of space. This other graph came from astronomers who study the blazing light from stars and shows the abundances of the different types of atoms in the universe. By far the most common atom of all is that of hydrogen, followed closely by helium, but not a great deal of anything else. Now look at this, it really is of cosmic significance. Both graphs, the stability graph and the abundances graph, show the same strange but very noticeable peak in exactly the same place. The first scientists who spotted this were blown away. One graph from the tiny nucleus and the other from the vastness of space point to the same magical atom, the atom that provided the key to unlocking the secrets of the entire universe.
Iron, the atom which was the key to understanding the atomic nucleus, also turned out to be one of the most abundant atoms in the entire universe. Amazingly, the properties of its nucleus seem to lead directly to how much of it there is. And it's not just true of iron. Radium, which is very unstable, turns out to be incredibly rare. Aluminium, which is relatively stable, turned out to be relatively common. It's a pattern which appears right across the list of elements. The signature of their nuclei is written in the skies above us. And deciphering the meaning of this connection would require the greatest minds of a generation. The first of these was a rebel and a maverick called Fred Hoyle. He loved walking the hills and dales of his native Yorkshire. Hoyle always spoke his mind, even though it brought him into conflict with his peers. He became something of a scientific pariah. More than almost any other scientist, he explored the strange overlap between the science of the atom and the science of the cosmos. Hoyle realized what the graphs revealed is that the underlying theme of the universe was ultimately change. Everything in the universe is in a state of flux. the atoms are trying to gain or lose protons in an attempt to become more stable. What Hoyle and his colleagues did was to ask how and where in the cosmos all this atomic transformation, all this alchemy, takes place. Hoyle knew that in stars like our Sun, hydrogen turns into helium by a process called nuclear fusion. But could nuclear fusion also be the way all the other atoms in the universe are made?
Fred Hoyle's great insight was to work out precisely how the heaviest elements are created through nuclear fusion. Hoyle worked out that this process can only take place at unimaginably high pressures and temperatures of millions of degrees centigrade. In our universe, there's only one place where such conditions exist: in stars.
Fred Hoyle's problem was with the details. To explain how fusion could create atoms heavier than helium was tricky and complicated. Hoyle had to explain precisely how in the fierce heat inside stars, light atoms might fuse to become heavier ones.
In the 40s, Hoyle worked out that our Sun is hot enough to fuse atoms like oxygen, carbon, and nitrogen. But what about heavier atoms like copper, zinc, or iron? His calculations showed that they could be made inside stars, but these would have to be much hotter than our Sun, and he knew exactly where to find them.
These huge bloated stars near the end of their lives were called red giants. Astronomers had discovered that there were hundreds of millions of these monsters throughout the universe. Fred Hoyle reasoned that they were hot enough to allow weightier atoms to be fused. But there was still a problem.
Even the mighty red giants weren't hot enough to make the really heavy stuff, atoms like gold and uranium.
To make these heavier than iron atoms would mean forcing them to fuse together, becoming more and more unstable. It would require unimaginable temperatures and pressures.
His only hope was that somewhere out there in the vastness of space were things so big and so hot they made our Sun look like a birthday candle.
And towards the end of the Second World War, during a research trip to Southern California, Fred Hoyle found them.
This is the 100-inch telescope at the Mount Wilson Observatory outside Los Angeles. When it was first built in 1917, it was without doubt the largest telescope in the world. And it was while he was here he met up with the great astronomer Walter Baade, who told him about supernovae. Now, these are processes when massive stars explode with an incredible intensity. And in a flash of inspiration, Hoyle realized that here at last were the extreme conditions necessary to produce all the heavy elements.
What Baade was referring to was an explosion of simply cosmic scale. When the largest stars run out of hydrogen to fuse into helium, they come to the end of their lives, and they collapse under the weight of their own gravity, and then explode outwards. In a blinding flash of inspiration, Hoyle and his colleague William Fowler realized that supernovae might be the hottest places in the universe, hot enough to fuse together even the heaviest of atoms. Hoyle and Fowler had found the furnaces in which everything was made.
The discovery of how atoms are made in stars is surely one of humanity's greatest achievements, except for one glaring problem, one that Hoyle could never explain away, and it was this. Stellar nuclear fusion can explain how all the elements in the universe are made, except for two very important ones, the two simplest elements, hydrogen and helium.
In the 1940s, using increasingly accurate equipment, scientists found that a quarter of the sun was in fact helium, which was considerably more than they thought. They realized that to fuse that amount of helium would mean the sun would have to be burning at billions of degrees. But the truth was, the sun only burns at 15 million degrees. The sun just wasn't hot enough to have made all that helium.
In fact, it turns out that per cubic meter, the sun actually generates less heat than a human being. So I produce more heat than a piece of sun the same size as me. This means that the sun is just not hot enough to make all the helium we know that it contains.
If all the helium wasn't made in the sun, then where did it come from? And even more crucial was the question Hoyle was in denial about. If all the atoms in the universe started off as hydrogen, where did that come from? All that hydrogen and all that helium needed an explanation. This problem catalyzed one of the most vicious fights in post-war science. That's because it turned into a much bigger question. In fact, the ultimate question. Was the entire universe created in a single instant, or has it always been there? Nearly every post-war physicist was sucked into this controversy, but two men were at its center. One was Fred Hoyle. The other was an eccentric Ukrainian called George Gamow. 6'4", a practical joker and a refugee from Stalin's Russia. Another physicist said of Gamow, even when he's wrong, he's interesting. Both men would stake their careers on this mother of all physics battles. It all began innocently enough. Gamow had recently been appointed a professor at George Washington University and thought the hydrogen and helium riddle might be worth exploring.
This was George Gamow's office at the George Washington University. It's really pokey. It was here that Gamow worked on the problem of why there seemed to be too much helium gas in the sun than could be accounted for from the fusion of hydrogen. Gamow came up with the crazy idea that maybe most of this helium had been around before the sun was even formed.
This is the moment it gets controversial and leads us inexorably into a row over creation. For Gamow to assert that helium existed in the universe before the sun and the stars were formed, he had to come up with another place that was capable of making helium. Gamow knew wherever this process was, it needed to be staggeringly hot, a searing billion degrees centigrade, millions of times hotter than the sun. At this temperature, matter as we know it is ripped apart. Hydrogen nuclei move about manically, constantly colliding, making helium at a prodigious rate. But what cosmic event was capable of reaching such an epic, terrifying temperature?
To explain this, he used a speculative theory that was doing the rounds at the time that suggested that the whole universe had been created in a single cataclysmic explosion billions of years ago, a theory that today we call the Big Bang.
For decades, astronomers have known that the galaxies are flying away from each other at astonishing speeds. The universe is getting bigger. This means that in the past, the universe must have been much smaller. And in the very, very distant past, the entire universe must have been a tiny, almost infinitesimally minute dot. And the implication of this is a single moment of creation, an instant at which all matter, even time and space, came into being. In 1945, most scientists were uncomfortable with this idea, but not Gamow. he spotted that it might solve the mystery of the excess helium in the sun and stars.
Gamow worked out that if the entire cosmos was squeezed down to a tiny dot, it would be immensely hot. In the first few minutes after the creation, the universe would have been hot enough for hydrogen nuclei to squeeze together to make all the excess helium in the sun and stars. Now, after those first few minutes, the universe would have expanded and would have been too cool. But a few minutes were all Gamow needed. In that time, all the hydrogen and almost all the helium was made. That's about 98% of all the atoms in the universe today. Or as Gamow put it, our universe was cooked in less time than it takes to cook a dish of duck and roast potatoes.
But by arguing that the Big Bang, a deeply controversial idea, had created most of the hydrogen and helium in the universe, Gamow ignited an enormous row over creation. Fred Hoyle soon became the most vocal of Gamow's critics.
Fred Hoyle hated the idea of the Big Bang with every fibre of his being. You see, as a committed atheist, he objected to the theory because a single moment of creation to him smacked of a divine creator. Gamow hit back, saying that without the Big Bang, Hoyle couldn't properly explain why there was so much hydrogen and helium in the universe. Both men had their supporters, and the arguments between the rival camps became quite shrill and personal. Hoyle was deemed as an old-fashioned, crusty old Brit by the Big Bang supporters, and Gamow was condemned as a closet creationist by Hoyle supporters. The arguments raged in scientific conferences and in the popular press.
Secretly, each side knew that they had a compelling argument, but both lacked the killer piece of evidence that would settle things decisively. The conflict seemed destined to remain unresolved. Then, south of New York, close to the mean streets of New Jersey, an unlikely piece of equipment was to make one of the most important discoveries of the century and settle the argument once and for all.
This giant piece of sadly rusting machinery is the Bell Labs horn antenna in New Jersey. It's in fact a radio telescope. But rather than looking like the more traditional satellite dish, it has this huge horn-like structure that could be rotated round to face the sky and pick up radio signals from space. It's a bit like a giant hearing aid, but it could pinpoint very, very weak signals extremely accurately. It was originally built for research into satellite communication. But instead, it was used in the mid-1960s to make one of the most important discoveries in the history of science.
Two researchers, Arno Penzias and Robert Wilson, had got hold of this antenna in 1963 from Bell Laboratories, with the intention of doing research into the faint halo of hydrogen around the Milky Way.
Before Penzias and Wilson could begin their experiment, they had to make sure they got rid of all the background noise the antenna was picking up. It's a bit like the hiss on radios in between stations. They spent the best part of a year checking all the equipment and the electronics. They even got down on their hands and knees inside the dish to scrub it clean of what they called white dielectric material, which is basically pigeon crap. But even after all this, there was still a faint, persistent hiss they couldn't get rid of, and it was there whichever direction the antenna pointed.
There was only one viable explanation. The noise was the sound of radiation, the afterglow of Gamow's Big Bang. Here at last was final proof that Gamow was right. The Big Bang had to have happened.
You see, soon after the universe was created, about 300,000 years after the Big Bang, it had expanded and cooled enough for the atoms of the lightest elements to form, leaving the whole universe awash with light. Now, George Gamow had earlier predicted that this afterglow of creation would today be in the form of weak microwave radiation. You can actually hear this radiation as a tiny fraction of the hiss on your radio or TV in between channels. The detection of this cosmic background radiation by Penzias and Wilson showed that Gamow's Big Bang theory was correct, and that he was right about how hydrogen and helium were formed in the early universe. So this, together with Hoyle and Fowler's theories about how the atoms of all the heavier elements were cooked inside stars, gave us the complete picture. We finally understood how the atoms of all the elements in the universe were made.
In less than 100 years, science has performed a miracle. It had truly explained where we come from and was able to describe the entire 14 billion year history of the cosmos. In the beginning was the Big Bang, an explosion of unimaginable power. In the following 10 minutes, in the searing heat, the nuclei of just two types of atom emerged, hydrogen and helium. For the next 300,000 years, the universe expanded. At that point, another cosmic chapter began. Individual atoms separated out from each other. As they did this, they released light. It's the remnants of this light that Penzias and Wilson picked up with their horn antenna. Then, millions of years after this, massive clouds of hydrogen coalesced into the first stars. In here, they began to fuse, producing starlight, and eventually all the other types of atoms that exist in the universe today.
Our Earth and everything on it, including our own bodies, was forged long ago in the crucibles of space. For instance, my body is almost 3/4 water, which we know is made up of oxygen and hydrogen atoms. We now understand that hydrogen was formed 13 billion years ago, soon after the Big Bang itself, whereas oxygen had to wait to be cooked inside stars, like our sun. The same is true of another important element in my body, carbon, the element on which all life forms on Earth are based. But my body also contains other elements in smaller amounts, like iron. This element was formed during the dying embers of gigantic stars as they ground towards the ends of their lives. There are also trace elements, like zinc. There are only 2 grams of zinc in my body, but this element had to be created during a supernova, the explosion of a giant star with cosmic violence, during which lighter atoms are fused together to form heavier elements. The same is true for all naturally occurring elements. They're all cooked in cosmic cauldrons. Romantically, you could say that we're all made of stardust. But the truth is also that we're all just nuclear waste. This is the story of the greatest scientific discovery ever. The discovery that everything is made of atoms. The vast variety and richness of everything we see around us in the world and beyond, how it's built up, how it all fits together, is all down to atoms and the mysterious laws they obey. As scientists delve deep into the atom, into the very heart of matter, they unraveled nature's most shocking secrets. They had to abandon everything they believed in and create a whole new science. A science that today underpins the whole of physics, chemistry, biology, and maybe even life itself. But for me, the story of how humanity solved the mystery of the atom is both inspiring and remarkable. It's a story of great geniuses, of men and women driven by their thirst for knowledge and glory. It's a story of false starts and conflicts, of ambition and revelation, a story that leads us through some of the most exciting and exhilarating ideas ever conceived of by the human race. And for a working physicist like me, it's the most important story there is. On the 5th of October 1906, in a hotel room near Trieste, a German scientist called Ludwig Boltzmann hanged himself. Boltzmann had a long history of psychological problems, and one of the key factors in his depression was that he'd been vilified, even ostracized, for believing something that today we take for granted. He believed that matter cannot be infinitely divisible into ever smaller pieces. Instead, he argued that ultimately, everything is made of basic building blocks, atoms.
It seems incredible now that Boltzmann's revelation was so controversial. But 100 years ago, arguing atoms were real was considered by most to be a waste of time. Although philosophers since the Greeks had speculated that the world might be made out of some kind of basic unit of matter, they realized that they were far too small to see, even under the most powerful microscopes. Speculating about them was therefore a complete waste of time. But then, in the middle of the 19th century, whether or not the atom was real was suddenly a question of burning importance. The reason was this: steam.
By the 1850s, it was changing the world. It powered the mighty engines, the trains, the ships, the factories of the Industrial Revolution. So figuring out how to use it more effectively became a matter of crucial commercial, political, and military significance. Not surprisingly then, it became the key question of 19th century science.
The demand to build more powerful and efficient steam engines in turn created an urgent need to understand and predict the behavior of water and steam at high temperatures and pressures. Ludwig Boltzmann and his scientific allies showed that if you imagine steam is made of millions of tiny rigid spheres, atoms, then you can create some powerful mathematical equations. And those equations are capable of predicting the behavior of steam with incredible accuracy.
But these same equations plunged Boltzmann and his fellow atomists into controversy. Their enemies argued that since the atoms referred to in their calculations were invisible, they were merely a mathematical convenience rather than real physical objects. To claim that imaginary entities were real seemed presumptuous, even blasphemous. You see, Boltzmann's critics argued that it was sacrilegious to reduce God's miraculous creation down to a series of collisions between tiny inanimate spheres. Boltzmann was condemned as an irreligious materialist. The tragic irony of Boltzmann's story is that when he took his own life in 1906, he was unaware that he'd been vindicated. You see, a year before he died, a young scientist had published a paper which undeniably, irrefutably proclaimed the reality of the atom. You might have heard of this young scientist. His name was Albert Einstein.
In 1905, the year before Boltzmann's suicide, Albert Einstein was 26 years old. His brash arrogance had upset most of his professors and teachers, and he was barely employable. Then he got his girlfriend pregnant. That was followed by a hasty marriage. He needed a job, any job.
Having not quite distinguished himself at university, he took up a job as a patents clerk here in Bern in Switzerland. He'd moved into this small one-bedroom apartment on Kramgasse with his young wife, Maleba.
Despite dire personal straits, the young Einstein had a burning ambition. He was desperate to make his mark as a physicist. And in 1905, during one miraculous year, the mark he made was truly incredible.
Having an undemanding job meant that young Einstein had plenty of time on his hands, both at work and here in this tiny apartment, to think deep thoughts. In the space of just a few months, he was to publish several papers that would change science forever. Now, everyone's heard of his theory of relativity, even if they don't understand it. And his paper on the nature of light was to win him the Nobel Prize a few years later.
But ironically, it wasn't either of these two papers that had the most impact on the discovery of atoms. The one that made all the difference was a short paper on how tiny grains of pollen danced in water.
Almost 80 years earlier, in 1827, a Scottish botanist called Robert Brown sprinkled pollen grains in some water and examined it through a microscope. What he found was really strange because instead of the pollen grains floating gently in the water, they danced around furiously, almost as though they were alive. Now, while this so-called Brownian motion was strange, scientists soon forgot about it. They found it mundane, even boring. I mean, who cared if the pollen jiggled about in the water?
And what had the jiggling to do with atoms anyway? For nearly 80 years, Brown's discovery remained a little-known scientific anomaly. Then, Einstein changed everything.
In one staggering insight, Einstein saw that Brownian motion was all about atoms. In fact, he realized that the jiggling of pollen grains in water could settle the raging debate about the reality of atoms forever.
His argument was simple. The pollen will only jiggle if they were being jostled by something else. So Einstein said that the water must be made of tiny atom-like particles, which themselves are jiggling and are continually buffeting the pollen. If there were no atoms, then the pollen would stay still.
So Boltzmann and his contemporaries had been rowing furiously about this question for nothing. The answer was there all along. Einstein proved that for Brownian motion to happen, atoms must exist. Einstein's paper went way beyond just verbal arguments. With flawless mathematics, he proved that the dance of the pollen revealed the size of the atom. And it's mind-numbingly tiny, 1/10 of a millionth of a millimeter across. A single human hair, itself one of the narrowest things visible to the naked eye, is over 1 million atoms wide. Let me put it another way. There are more atoms in a single glass of water than there are glasses of water in all the oceans of the world. It sort of hurts your head just to think about it.
Einstein's paper ended the debate about whether the atom was real or not, and Boltzmann had been totally vindicated. The atom had to be real.
By the early years of the 20th century, the atom had arrived. Scientists who'd argued that the atom was real were no longer heretics. In a dramatic, sudden reversal, they became the new orthodoxy. But they were to pay a huge price for their success. Before they'd even had a chance to congratulate each other on discovering the atom, it ripped the rug out from under their feet and sent them spiraling into a bizarre and at times terrifying new world. And it all kicked off here, in what, by 1910, was the world's centre for atomic physics, Manchester. Two of the most extraordinary men in the history of science worked here in the physics department of Manchester University between 1911 and 1916. They were Ernest Rutherford and Niels Bohr. On the face of it, two very different personalities and the unlikeliest of collaborators.
Rutherford was from a remote part of New Zealand and grew up on a farm. Bohr was born in Copenhagen, wealthy and erudite, virtually an aristocrat. Rutherford was the ultimate experimentalist. He loved technology and ingenious arrangements of batteries, coils, magnets, and radioactive rocks. But he was also blessed with a profound intuition. In contrast, Bohr was the ultimate theoretician. To him, science was about deep thought and abstract mathematics. Pen and paper, chalk and blackboard were his tools. Logic was his path to truth. Although their approaches to their work couldn't have been any more different, they had one thing in common.
They were prepared to ditch 3 centuries of scientific convention if it didn't fit what they believed to be true. They were genuine revolutionaries. Rutherford and Bohr were two of the most extraordinary minds ever produced by the human race. But it would take every bit of their dogged tenacity and inspirational brilliance to take on the atom.
In 1907, Ernest Rutherford took over the physics department in Manchester. This was a period of momentous scientific change. Just over 10 years earlier, in Germany, came the first demonstration of weird rays that see through flesh to reveal our bones. These rays were so inexplicable, scientists didn't know what to call them, so they were named X-rays. And a couple of years after that, in Cambridge, it was shown that powerful electric currents could produce strange streams of tiny glowing charged particles that were called electrons. And in 1896 in Paris came the most significant discovery of all, one that more than any other would unlock the secrets of the atom. The metal uranium was shown to emit a strange and powerful energy that was named radioactivity. It seemed straight out of science fiction. Radioactive metals were warm to touch. They could even burn the skin. And the rays could pass through solid matter as if it wasn't there. It truly was a marvel of the modern age.
Rutherford was obsessed with radioactivity. All sorts of questions plagued him. How was it made? Why did it come in different forms? How far could it travel through a vacuum or through air? Did it alter the materials that it encountered? In Manchester, together with his assistants Hans Geiger of Geiger counter fame and Ernest Marsden, he devised a series of experiments that would probe the enigma of radioactivity.
1909, Manchester University. These are the props. Gold leaf beaten till it's just a few atoms thick. a movable phosphorescent screen that flashed when struck by radioactive rays. And inside this box is the star attraction, a tiny piece of the metal radium. Radium is an extraordinarily powerful source of a kind of radioactivity that Rutherford had named alpha rays. They weren't really rays, they were more like a steady stream of particles, and radium spat out these particles like a machine gun that never ran out of bullets. Rutherford set his students a simple enough task. Use the radium gun, shoot the alpha radioactivity at the gold leaf, and with the phosphorescent plate, count the number of particles that come out the other side. In practice, that meant sitting alone in the dark and counting tiny, almost invisible flashes on the phosphorescent screen. It was deeply tedious, but Rutherford insisted that they keep at it. Weeks passed and the team of researchers found nothing unusual. The alpha particles seemed to punch through the gold almost as though it wasn't there. Very occasionally, they would swerve slightly as they went through. Hardly front-page news.
Now comes what must be the most consequential off-the-cuff remark in the history of science, one that changed the world. The story goes that Rutherford bumped into his assistant Geiger in the corridor outside the lab. Geiger reported that so far they'd seen nothing unusual. Now, in response, Rutherford could have easily just nodded and walked on, but he didn't. He later claimed that he said what he said at the time for the sheer hell of it. But I don't believe him. Rutherford had great scientific intuition, and I think he had a hunch that something was about to happen. Here's what he said to Geiger. Tell young Marsden to go back and see if he can detect any alpha particles on the same side of the gold leaf as the radium source. In other words, see if any alpha particles are bouncing back. Now, it's an extraordinary suggestion from Rutherford and one that he had no logical reason to make. After all, Geiger and Marsden had spent weeks seeing the alpha particles do nothing but stream straight through the gold leaf, almost as though it wasn't there. Why would any bounce back? But Geiger and Marsden were young and in awe of the big New Zealander. They did their master's bidding and went back into their dark lab and watched patiently. For days, they saw absolutely nothing. They strained their eyes to the point of myopia, but didn't see a single alpha particle bouncing back off the gold. It seemed that Rutherford's suggestion really was a stupid one. But then the impossible happened. One afternoon in 1909, Geiger burst into Rutherford's office with some astonishing news. Very, very occasionally, an alpha particle would indeed ricochet back off the gold leaf. Geiger calculated that only 1 in 8,000 alpha particles would do this. It's a tiny percentage, but Rutherford's mind reeled with the news. He would later say it was like firing a shell at a piece of tissue paper and have it bounce back at you. There and then, Rutherford knew he'd struck physics gold. Although it would take him over a year to fully understand why the alpha particles would do this, when he did, he would show humanity for the first time the inside of an atom. Now, people had barely got used to the idea that atoms existed. But now, Rutherford knew that this minute world, 1/10 of a millionth of a millimeter across, had its own internal structure. Within the atomic, there's a subatomic world. And Ernest Rutherford believed he knew what it looked like.
Rutherford realized that the bouncing alpha particle revealed an atom that was totally unexpected. It had no familiar analogy on Earth. So Rutherford looked for one in the heavens. He pictured the atom as a tiny solar system. Electrons, tiny particles of negative electricity, orbit around a minute, positively charged object called the nucleus. Rutherford calculated that the nucleus was 10,000 times smaller than the atom itself. That's why only 1 in 8,000 alpha particles bounce back. They're the ones that hit the tiny nucleus by chance. The rest whiz by without hitting anything. The first astonishing consequence of this idea is that Rutherford's atom is almost entirely empty space. That's why nearly all the alpha particles race through the gold atoms as if there's nothing there. There really is nothing there.
Consider the bizarre implications of Rutherford's atom by imagining it on a bigger scale. If the nucleus were the size of a football, then the nearest electron will be in orbit half a mile away. The rest of the atom will be completely empty space. Let me explain it another way. If you were to suck out all the empty space from every atom in my body, then I would shrink down to a size smaller than a grain of salt. Of course, I'd still weigh the same. And if you did the same thing to the entire human race, then all 6 billion of us would fit inside a single apple. The atom was unlike anything we had ever encountered before, and it would only get stranger and stranger.
Almost immediately, a problem surfaced, and it was a big one. According to the tried and trusted science of the time, the electrons should lose their energy, run out of speed, and spiral into the nucleus in less than a blink of an eye. Rutherford's atom contradicted the known laws of science.
The atom didn't care that it defied scientific convention. It's almost entirely empty space, and it's going to stay that way. I show no signs of shrinking down to the size of a grain of salt. And the Earth is, well, the size of the Earth. It's not getting smaller.
Not surprisingly, all the established scientists of the day, including Einstein, were baffled. Scientific ideas they'd put their faith in all their lives had failed completely to explain the atom. The atom now required a new generation of scientists to follow in Rutherford's footsteps. Bold, brilliant, and above all, young. It was crucial they had no loyalty or attachment to ideas held by previous generations. One of the first of this new breed was Niels Bohr. He sailed from Denmark in 1911 and made his way to English soil.
Having finished his studies in Copenhagen, Bohr decided to move abroad and be at the centre of the new physics.
The trail led him to Britain, Manchester University, and Ernest Rutherford. Bohr made it his mission to solve the puzzles of why the atom didn't collapse and why there was so much empty space. As one of the new breed of theoretical physicists, he was fearless in his thinking and was prepared to abandon common sense and human intuition to find an explanation. So, in a leap of genius, he started to look for clues about the atom's structure, not by looking at matter, but by examining the mysterious and wonderful nature of light.
Now, atoms and light are clearly connected. Most substances glow when they're heated. And for centuries, people had realized that different substances glow with their own distinctive colors, a bit like a signature. So the green of copper, the yellow of sodium, and the red of lithium. These colors associated with different substances are called spectra. And Bohr's great insight was to realize that spectra are telling us something about the inner structure of the atom, that they could explain all that empty space. Bohr's idea was to take Rutherford's solar system model of the atom and replace it with something that's almost impossible to imagine or visualize. So sensible ideas like empty space and particles moving around in orbits fade away. And they're replaced with something that is one of the most misunderstood and misused concepts in the whole of science, the quantum jump. Now, it takes most working physicists many years to come to terms with quantum jumps, and in fact, Bohr himself said that if you think you've understood it, then you haven't really thought about it enough. So I'm going to take a deep breath and in under 30 seconds try and explain to you one of the most complicated concepts in the whole of science, but one that underpins the entire universe. Bohr described the atom not as a solar system, but as a multi-story building. The ground floor is where the nucleus lives, with the electrons occupying the floors above. Mysterious laws mean the electrons can only live on the floors, never in between. And other mysterious laws mean that sometimes they can instantaneously jump from one floor to another. These are what we call quantum jumps. Now, Bohr had absolutely no idea what these laws were, but thinking like this allowed him to make a startling prediction. When an electron jumps from a higher floor to a lower one, it gives off light. More significantly, the colour of the light depends on how big or small a quantum jump the electron makes. So, an electron jumping from the third floor to the second floor might give off red light. An electron jumping from the 10th floor to the second floor, blue light. To test his new theory, Bohr used it to make a prediction. Could it explain the mysterious signature in the spectrum of hydrogen? After months of calculating furiously, he finally came up with a result. And his prediction was surprisingly accurate. For the first time ever, it looked like the spectrum could be explained. And back in 1913, that was big news. But Bohr's new idea rested on a single, seriously controversial supposition. Why should the electrons in the atom behave as though they were in a multi-story building? And why should they magically perform quantum jumps from one story to another? There was no precedent for it anywhere else in science. When one physicist claimed that the jumps were nonsense, Bohr replied, yes, you're completely right, but that doesn't prove the jumps don't happen, only that you cannot visualize them. But not being able to visualize things seemed to go against the whole purpose of science. Older scientists in particular felt that science was supposed to be about understanding the world, not about making up arbitrary rules that seemed to fit the data. Conflict between the two generations of scientists was inevitable. Bohr's weird new atom and his crazy quantum jumps were a shot across the bow of traditional classical science, and the old school reacted angrily. Leading the traditionalists was giant of the physics world Albert Einstein. He hated Bohr's ideas, and he was going to fight them. Anything to save the world of order and common sense from this assault by madness. Bohr, though, was undeterred, and as the 1920s dawned, the battle lines for one of the greatest conflicts in all science were drawn. So far, the debates about the new atomic physics had been polite and gentlemanly. Now, the two sides wheeled out their biggest guns, two of the greatest names in physics. There were two very contrasting characters who loathed each other. For the new revolutionary science was a buttoned-up, uber-competitive German called Werner Heisenberg. For the conservatives was a debonair, Byron-esque Austrian called Erwin Schrodinger. Erwin Schrodinger, passionate and poetic, a philosopher and a romantic. He wrote books on the ancient Greeks, on philosophy, on religion. He was influenced by Hinduism. He was also a very flamboyant character, cool, suave, sophisticated, a dapper dresser, and a big hit with the ladies. Schrodinger's promiscuity was legendary. He had a string of girlfriends throughout his married life, some of them much younger than him. In 1925, 38-year-old Schrodinger stayed at the Alpine resort of Arosa in Switzerland. for a secret liaison with an old girlfriend, whose identity remains a mystery to this day. But their passion proved to be the catalyst for Schrödinger's creative genius.
Another physicist said of Schrödinger's week of sexually inspired physics, he had two tasks that week: satisfy a woman and solve the riddle of the atom. Fortunately, he was up to both. He took de Broglie's idea of mysterious pilot waves guiding electrons around an atom one crucial step further. He argued that the electron actually was a wave of energy, vibrating so fast it looked like a cloud around the atom, a cloud-like wave of pure energy. And what's more, he came up with a powerful new equation which completely described this wave, and so described the whole atom in terms of traditional physics.
The equation he came up with we now call Schrödinger's wave equation. It's incredibly powerful. What's unique about it is that it features a new quantity called the wave function, which Schrödinger claimed completely described the behavior of the subatomic world.
Schrödinger's equation and the picture of the atom it painted, created during a sexually charged holiday in the Swiss Alps, once again allowed scientists to visualize the atom in simple terms. It's hard to overestimate the relief Schrödinger's idea brought to the traditional physics community. Strange though his picture of the atom was, at least it was a picture. And scientists love pictures. They allowed them to use their intuition.
But there was still a deep, nagging problem, one that the radicals felt Schrödinger just couldn't reconcile. His new theory still couldn't account for Bohr's strange, instantaneous quantum jumps. The time had come for the radicals to hit back.
In the summer of the same year, one of Niels Bohr's protégés, Werner Heisenberg, was travelling to an obscure island off the north coast of Germany. He was fiercely competitive and took Schrödinger's ideas as a personal affront. He felt strongly that the strangeness of the instant quantum jumps was actually the key to understanding the atom. He thought the atom was so unique and unusual it shouldn't be compromised through a simple analogy like a wave or an orbit or even a multi-story building. He believed it was time to give up any picture of the atom at all.
Werner Heisenberg, one of the true geniuses of the 20th century. Young, athletic, a great mountain climber, an excellent pianist, he was also an exceptional student. At the age of just 20, he was well on his way to finishing his PhD and being courted by the great universities across Europe. Now, in the summer of 1925, he was suffering from a particularly bad bout of hay fever. His face was swollen up almost beyond recognition. He decided to escape alone here to this beautiful but isolated island of Helgoland. He walked along the beaches, he swam, he climbed the rocks, and he pondered.
Ever since he'd encountered atomic physics, Heisenberg felt in his bones that all human attempts to visualize the atom, to model it with familiar images, would always fail. The atom, he believed, was too capricious, too strange to ever be explained that simply. So he decided to abandon all pictures of it and describe it using pure mathematics alone. But as he pondered, he realized that the atom didn't just defy visualization, it even defied traditional mathematics.
It was while he was here on Helgoland that Heisenberg had an incredible revelation. He realized that in order to describe certain properties of atoms, he had to use a strange new type of mathematics. It seems that certain properties like where an electron is at a given time and how fast it's moving, when multiplied together, the order in which you multiply them matters. Let me try and explain. If we multiply two numbers together, it doesn't matter which order we do it in. So 3 times 4 is clearly the same as 4 times 3. But when it came to atoms, Heisenberg realized that the order in which he multiplied quantities together gave a different answer. This quickly led him to other discoveries, and he was convinced that he'd cracked a code in the atom, that he'd somehow found the hidden mathematics within. He was so excited. He was also very scared. That night, he climbed to the top of a rock and sat there waiting till dawn. He called it his night of Helgoland. When he returned to his university in Göttingen, he told his colleague Max Born about it, and they then worked together intensely for several months, developing a whole new theory of the atom, a theory that today we call matrix mechanics.
Matrix mechanics uses complex arrays of numbers, rather like a spreadsheet. By manipulating these arrays, Heisenberg and his mentor, the brilliant physicist Max Born, could accurately predict atomic behavior. But for Einstein and the traditionalists, this was pure scientific heresy. An atom can't actually be a matrix of numbers. Surely we're made of atoms, not numbers.
Back in Copenhagen, Bohr and Pauli were thrilled with matrix mechanics. So what if we couldn't imagine the atom as a physical object? They exulted in the purity of the mathematics and launched into vicious attacks against Schrödinger's vulgar sensual waves. Heisenberg wrote, "The more I reflect on the physical portion of Schrödinger's equation, the more disgusting I find it. In fact, it's just bullshit." But Schrödinger was equally scathing of Heisenberg, saying he was repelled by his methods and found his mathematics monstrous.
In Munich in 1926, their enmity began to reach boiling point. Schrödinger was to give a lecture on his wave equation. Heisenberg scraped together the money to travel down to Munich for the lecture, to finally come face to face with his rival. What was at stake was more than just Heisenberg's reputation. He believed Schrödinger's simplistic approach wasn't just misguided, but totally wrong. And his intention was nothing less than to destroy Schrödinger's theory.
Schrödinger delivers his lecture on the new wave mechanics to a packed audience. They're standing room only. He writes down his new wave equation. To Schrödinger, this describes a real physical picture of the atom, with electrons as waves surrounding the atomic nucleus. 24-year-old Werner Heisenberg is in the audience. He can hardly contain himself. At the end of the lecture, he stands up and delivers a monologue attacking Schrödinger's approach. For Heisenberg, it's impossible to ever have a picture of what the atom is really like. The audience is on Schrödinger's side. They much prefer his simple physical interpretation to Heisenberg's abstract, complicated mathematics. Heisenberg is booed. He's told to sit down and be quiet. He leaves the lecture sad and depressed.
Heisenberg returned to Copenhagen with his confidence severely dented. There at the Institute, he and Bohr reached their darkest moment. Almost all of the scientific community was against them. They felt isolated, desperate. Their backs were against the wall. Despite this, they stubbornly refused to give up their controversial theory.
This attic room was Heisenberg's study back in 1926. Bohr would come up here night after night, where he and Heisenberg would argue about the meaning of the new quantum mechanics. they would argue so passionately that on one occasion, apparently, Heisenberg was reduced to tears.
And then, as Heisenberg stared out of his attic window in despair at the park below, an extraordinary thought occurred to him. It struck him why an atom can't be visualized, why it can't be understood intuitively. It's not just because it's tiny, tricky and difficult. It's because it's inherently unknowable.
He realised that there was a fundamental limit to how much we can know about the subatomic world. For instance, if we know where an electron is at a particular moment in time, then we cannot know how fast it's moving. But if we knew its speed, we wouldn't know its position. This ambiguity isn't a shortcoming in the theory itself, nor is it due to the clumsiness of the way we carry out our measurements, but a fundamental truth about the way nature behaves at the subatomic scale. It became known as Heisenberg's uncertainty principle, and is probably the most profound, incredible, yet unsettling concepts in the whole of science.
What Heisenberg had uncovered through his abstract matrix mechanics was a deep and shocking truth about the atomic world. Atoms are willfully obscure. We can never fully know an atom's position and speed simultaneously. The atomic world just refuses to allow that to happen. It was completely mind-boggling. But once they accepted it, Heisenberg and Bohr found the boost of confidence to be even more bold. They realized uncertainty forced them to put paradox right at the very heart of the atom.
Atoms are not just unimaginable, they're self-contradictory. They behave both like particles and waves. And it gets weirder. When you're not looking at an atom, it behaves like a spread-out wave. But when you look to see where it is, it behaves like a particle. This is insane. First, atoms couldn't be visualized at all. Now it seems they change completely in character depending on whether or not you're looking at them.
The uncertainty principle had changed everything. It revealed a shocking contradiction at the heart of nature. Everything we see is made of atoms, and yet atoms themselves are unknowable. They can only be understood through mathematics. For the first time for Bohr and Heisenberg, everything about the atom fell into place. By the autumn of 1927, full of confidence and smarting for a fight, they knew they were finally ready to take on the conservatives. For this physics showdown, they chose the Solvay Conference in Brussels. All the world's leading atomic physicists would attend. If Bohr and Heisenberg were successful, then they would lead a total scientific revolution.
This is amazing. I'm looking at original footage of the Solvay delegates coming out of these doors. There's Bohr talking to Schrodinger, and there's Heisenberg behind them. And there's Pauli, strange-looking guy. Oh, and there's Einstein coming down with a big smile on his face.
For the week of the conference, all that the delegates could think and talk about was Bohr's quantum mechanics. With uncertainty now a central plank, it was a truly formidable theory. And over the week, the final showdown played out between Bohr and his arch-rival Albert Einstein.
Einstein hated quantum mechanics, and every morning he'd come to Bohr with an argument that he felt picked a hole in the new theory. Bohr would go away very disturbed and think very hard about it, and by the end of the day, he'd come back with a counter-argument that dismissed Einstein's criticism. And this happened day after day until by the end of the conference, Bohr had brushed aside all of Einstein's criticisms, and Bohr was regarded as having been victorious.
And with that, his vision of the atom, which became known as the Copenhagen interpretation, was suddenly at the very heart of atomic physics.
At the end of the conference, they all gather for the team photo. Never before or since have so many great names of physics been together in one place. At the front, the elder statesman of physics, Hendrik Lorentz, flanked on either side by Madame Curie and Albert Einstein. Einstein's looking rather glum because he's lost the argument. Louis de Broglie has also failed to convince the delegates of his views. Victory goes to Niels Bohr. He's feeling very pleased with himself. Next to him, one of the unsung heroes of quantum mechanics, the German Max Born, who developed so much of the mathematics. And behind them, the two young disciples of Bohr, Heisenberg and Pauli. Pauli's looking rather smugly across at Schrodinger, a bit like the cat who's got the milk. This was the moment in physics when it all changed. The old guard was replaced by the new. Chance and probability became interwoven into the fabric of nature itself, and we could no longer describe atoms in terms of simple pictures, but only using pure abstract mathematics. The Copenhagen view had been victorious.
Although Einstein went to his grave never believing quantum mechanics, Solvay 1927 was the turning point at which the rest of the science establishment came to embrace the Copenhagen interpretation. And that interpretation is still accepted today.
All the physics that I use in my research, certainly the quantum mechanics that I teach my students and that fills the textbooks on my shelves, is based on ideas that were hammered out and crystallized here at the Solvay Conference in October 1927. In a sense, everything I know about the way the world around me is made up started here.
The quantum mechanical description of the atom is one of the crowning glories of human creativity. Over the last 80 years, it has been proven right time after time, and its authority has never been in doubt. It's a monumental scientific achievement.
Between 1905 and 1927, science changed our view of the world. It also changed our view of science itself. As scientists probed the tiniest building blocks of matter, they created the most successful and powerful theory ever, quantum mechanics. It allows us to describe what everything in the universe is made of, how it interacts, and how it all fits together. But it comes at a huge price. At its most fundamental level, we have to accept that nature is ruled by chance and probability. Heisenberg's uncertainty principle dictates that there are certain limits on the sorts of questions we can ask the atomic world. And most crucially, while we now know so much more about what an atom is and how it behaves, we have to give up any possibility of imagining what it looks like. Our human nature has forced us to ask questions of everything we see around us in the world. What we've discovered has been beyond our wildest imagination. In 1912, in a hot air balloon about 3 miles above the ground, an Austrian scientist called Victor Hess made one of the most astonishing discoveries in science. Up here,
tests found that incredibly mysterious rays of energy were pouring in from outer space and streaming through the Earth. They were incredibly powerful and yet unlike anything anyone had ever seen before. They were called cosmic rays. At the same time, in laboratories down below, scientists were studying equally mysterious and equally powerful rays of energy, pouring out from the interior of atoms, energy known as radioactivity. Mysterious rays from the vast emptiness of space, and mysterious rays from deep within the atom, the tiniest building block. No one really understood what they were, let alone believe that they might be connected. Then an incredible story unfolded. Cosmic rays and radioactivity turned out to be connected in a way so shocking that it beggars belief. The discovery of this connection would force us to rethink the nature of reality itself. The world we think we know, the solid, reassuring world of our senses, turns out to be just a tiny sliver of an infinitely weirder, more wonderful universe than we could have ever conceived of in our wildest fantasies. Our reality is just an illusion.
In the years up to the mid-1920s, the atom revealed its strange secrets to us at a prodigious rate, as it produced one scientific revolution after another. In 1897, Marie Curie studied strange rays pouring out of some rare metals. She called them radioactivity. Then, in 1905, Albert Einstein conclusively proved the existence and size of an atom by studying the way pollen moves in water. A few years later, the New Zealander Ernest Rutherford performed an experiment in Manchester that revealed to him the shape of the interior of an atom. Scientists were shocked to discover that the atom is almost entirely empty space. The question then became, how could this empty atom possibly make the solid world around us? The answer to that was worked out by a group of revolutionary physicists in Denmark. They proposed that the world of the atom ran on principles which were completely different to any mankind had ever seen before. It meant that the atom, the basic building block of everything in the universe, was unique and perhaps outside human comprehension. Then, as scientists explored the nucleus, the tiny heart of the atom, they found it bursting with powerful energy. This discovery gave them the potential to bring about the destruction of the Earth. But in a shocking turnaround, it also gave them a fundamental understanding of how the universe itself was created. And yet, despite this, the journey to understand the strange and capricious atom had only just started. In 1927, a young man was studying at the mathematics department of Cambridge University. Shy, awkward, clumsy, and frighteningly brilliant. His name was Paul Adrien Maurice Dirac.
It's probably fair to say that Paul Dirac isn't a household name, but he should be. He was recently voted by other physicists as the second greatest English physicist of all time, second only to Isaac Newton.
And he deserves the accolade. All the brilliant minds that pioneered atomic physics were left trailing by Dirac, aghast at the sheer boldness and lateral thinking in his work. When Einstein read a paper by the then 24-year-old Dirac, he said, "I have trouble with Dirac. This balancing on the dizzying path between genius and madness is awful. In 1927, for reasons no one has ever really fathomed, Paul Dirac set himself a task which was monumental in its scope: to unify science, to bring its scattered parts into one beautiful entity. And what this meant, above all, was to unite the two most difficult and counterintuitive ideas in history.
Here's what Dirac was trying to reconcile. First, there's quantum mechanics, a set of mathematical equations that describe the atom and its component parts. Then there's Einstein's special theory of relativity, which at first glance seems completely unrelated to the atom. It deals with loftier matters like the nature of space and time themselves. One of its consequences is that objects behave very differently when they travel close to the speed of light. The first thing you might ask is, why would anyone want to reconcile two such different theories? Well, by the late 1920s, the equations of quantum mechanics were consistently getting the wrong answers when describing electrons, one of the constituents of atoms, as they move at very high speed. But for Dirac, there was a much more esoteric motivation. He was once quoted as saying that a physical theory must have mathematical beauty. So for him, the fact that quantum mechanics and relativity weren't reconciled wasn't just inconvenient, it was downright ugly.
So around 1925 in Cambridge, Dirac put his extraordinary mind, a mind that even Einstein had trouble keeping up with, to work.
This is room A4 of New Court, and it was Dirac's original study. I guess the original fireplace has been boarded up now, but it was here that Dirac tried to understand and bring together the two new ideas of 20th century physics. Now, word is Dirac would sit here in front of his blazing fireplace and try and understand and bring together these two different theories into one unified picture, one single equation.
For 3 frustrating years, he laboured alone on the problem. Then, one evening in early 1928, he had an amazing revelation.
The only way I can explain what happened is to say that the equations of quantum mechanics and special relativity coalesced inside Dirac's mind. Einstein's description of space and time somehow stretched and squeezed the existing equations of the atom. They bent and twisted them into all sorts of new weird and wonderful shapes. Then, guided by his unshakable belief that nature's laws must be beautiful, Dirac honed in on one equation, an entirely new description of what goes on inside the atom.
Dirac knew it was right because it had mathematical beauty.
Here it is, the Dirac equation. Gamma mu into I d mu minus E a mu psi equals m psi. Don't try and understand it, just look at it and marvel. As far as human achievements go, it's up there with King Lear, Beethoven's Fifth, or The Origin of the Species. Because hidden in these symbols is the perfect description of how reality works at a fundamental level. It's the key to nature's secret code.
With perfect mathematical elegance, Dirac's equation describes an atomic particle travelling at any speed, right up to the speed of light.
That much Dirac was expecting to achieve. But when he looked at his own equation more carefully, he noticed something breathtakingly revolutionary about it. He later said his equation knew more than he did. In essence, Dirac's equation was telling him that there's another universe we've never noticed before. That's because instead of his equation having one answer, it has two. The first describes the universe we know, made of the atoms we're familiar with. The second describes a kind of mirror image to our universe, made of atoms whose properties are somehow reversed. Now, science fiction fans will know what's coming. As well as matter, Dirac's equation predicts the existence of antimatter.
Dirac's theory seemed to say that for everything in our known world, for every part of an atom, every particle, there can exist a corresponding antiparticle, with the same mass but exactly opposite in every other way. And just like a world in a mirror, a universe made of antimatter atoms would look and work just like ours.
It will be perfectly possible for me to be made entirely out of antimatter. Anti-me would look and behave exactly the same as original me. And indeed, it's possible that out there in the vast expanses of the cosmos, there are stars and planets and even living beings made out of antimatter. And there's one final prediction of the Dirac equation. As its punchline, it states that matter and antimatter must never come into contact, because if they do, they will annihilate each other in a fierce conflagration of pure energy. The combined mass of matter and antimatter would convert completely into energy, according to Einstein's famous equation, E equals mc squared. So, if I ever do meet my doppelganger, we would explode with an energy equivalent to 1 million Hiroshima-sized atom bombs.
All this sounds like science fiction. And indeed, the idea of antimatter has inspired huge swathes of it. But the truth is, antimatter, particularly antimatter electrons called positrons, are made routinely now in laboratories. Positrons are used in sophisticated medical imaging devices called PET scanners that can see through our skulls and accurately map pictures of our brains. But back in the 1920s, the initial reaction to Dirac's equation among physicists was deeply skeptical. Even Dirac himself had trouble believing his own results. Antimatter seemed such a preposterous concept. Then came resounding confirmation of the Dirac equation and all its paradoxical implications. And it came from the most unexpected place, outer space.
In 1932, physicist Carl Anderson was working here at Caltech in Los Angeles when he made an amazing discovery. He'd been studying cosmic rays. These are high-energy subatomic particles that continuously bombard the Earth from outer space. To do this, he used a device called a cloud chamber. This is basically a vessel that's filled with a fine mist of water vapor. This shows up the tracks of the particles as they stream down through the vapor. And placed inside a magnetic field, these tracks will be deflected one way or the other, depending on the electric charge of the particle. So positive particles' tracks bend one way, negative the other. Anderson found evidence of particles that look exactly like electrons, but which are deflected in the opposite direction. He had discovered Dirac's anti-electrons, particles of antimatter.
The Dirac equation is an impressive achievement. Its prediction of the existence of antimatter using abstract mathematics alone will be enough to make it a significant milestone in the history of human thought.
But within just a few years of publication, first Dirac and then others sensed that his new equation was telling them something profound, something completely new about nature. And they were right. But the revelation hidden within Dirac's equation would take the best efforts of the greatest minds 30 years to uncover.
The problem with Dirac's equation was this.
Although it was incredibly powerful and had led to the discovery of antimatter, ultimately it could only describe a single electron. It fails completely to explain what happens when there is more than one electron present. What was needed was a new theory, a theory which explains how electrons interact with each other. And that turned out to be the most difficult question of the mid-20th century. But when an answer came, it was to bring with it an unexpected revelation.
This office in Caltech, just outside Los Angeles, used to belong to the great Richard Feynman. In our story of so many geniuses of science, Feynman stands, in my view, second only to Einstein in the list of greatest 20th century physicists. You see, Feynman wasn't just a common or garden genius. Many referred to him as a magician. He was so smart, such an innovative thinker. And like Einstein, he became this mythical figure, certainly a household name. Feynman was a larger-than-life character. He had a huge personality. He loved cultivating and telling anecdotes about himself. He used to frequent strip clubs. He had affairs with his students. He was even rumoured to go to orgies. But his greatest contribution to physics was the part he played in developing the next phase of quantum mechanics.
Feynman and his contemporaries were attempting to pick up the atomic torch from Paul Dirac and develop a theory that took our understanding of the atom literally a quantum leap further. Like Dirac's antimatter equation before, the intention of the new theory was unification. They wanted to understand how electrons affect each other. In other words, it aimed to explain how everything works together through the electromagnetic field. They called their unification project Quantum Electrodynamics, or QED. The project was a formidable challenge, but the end result was magnificent. Nothing less than the most far-reaching and accurate scientific theory ever conceived.
For instance, it predicts a certain property of the electron, called its magnetic moment, to have a value of 2.002319304. Experiments measure precisely the same number. And that's an agreement between theory and experiment to 1 part in 10 billion. It's an unprecedented level of agreement. It's like measuring the distance between London and New York to within the thickness of a human hair.
The phenomenal accuracy of quantum electrodynamics shows it to underpin almost everything we experience in the physical world. It's as close to a theory of everything as we have ever come.
It defines the laws of nature at the atomic scale. It explains shape, color, texture, and the way almost everything interacts and fits together. It underpins and encompasses everything from the biochemistry of life to why we don't fall through the floor.
So what does QED actually say? Well, this is where the going gets very tough. It may be a wonderful scientific description of nature, but trying to understand what Richard Feynman was doing with his theory is almost impossible. This is what he himself said when he introduced his theory to the public. It is my task to convince you not to turn away because you don't understand it. You see, my physics students don't understand it. That's because I don't understand it. Nobody does.
If the inventor of the theory doesn't understand, what possible hope is there for the rest of us? With that disclaimer, I'm going to try and explain anyway. First, you have to abandon your most basic intuition about nature. You have to give up the notion that empty space is empty. Let me try and explain. If I were to suck out all the air from this jar, you'd quite rightly say that having removed all the atoms, I'm left with a vacuum, a volume of pure emptiness. Quantum electrodynamics flies in the face of this common sense idea.
by saying that the vacuum is not, I repeat, not a place where nothing exists and nothing happens. Instead, it's full of stuff and is heaving with activity. How can this possibly be true?
Well, let's imagine one tiny point in the emptiness. Common sense tells us there's nothing there, but quantum physics tells us there's only nothing there on average. And it's those two words, on average, that force us to rethink our understanding of reality. Think of empty space like a bank account, which on average has nothing in it. As a physics academic, this is a concept I'm very familiar with. Some days it might be £100 in credit, other days it might be £100 overdrawn, but on average it has a zero balance. Empty space turns out to have similar accounting skills, but it can borrow energy rather than money. And this energy is literally borrowed from the future, provided that it's paid back again very quickly. In practice, what this means is that the borrowed energy can be used to create a particle and an antiparticle, which are spontaneously formed from the void, provided that a fraction of a second later, they annihilate each other and disappear.
Energy is borrowed out of nowhere. It's turned into matter, the matter then self-destructs back into energy. And this happens in an instant all over the void. In fact, in a stunning confirmation of Dirac's antimatter theory, the vacuum seethes with huge numbers of matter and antimatter particles continually being created and annihilated.
Down at the smaller scale, space is a constant storm of creation and destruction. Physicists call it the quantum foam. The particles in the quantum foam come and go so quickly that we're completely unaware of them. We refer to them as virtual particles. But if we were able to slow time down almost to a standstill, we'd be able to see this seething activity, this constant creation and annihilation of matter and energy that's the fabric of reality itself. And from this comes the most jaw-dropping idea of all. Quantum electrodynamics says that the matter we think of as the stuff that makes up the everyday world, the world that we see and feel, is basically just a kind of leftover from all the feverish activity that virtual particles get up to in the void. So you, me, the Earth, the stars, everything is basically just a part of a deeper, infinitely more complex reality than we ever imagined.
Of course, when Feynman first started to develop his revolutionary ideas in Caltech in the mid-40s, his contemporaries were horrified. Because at that time, the general opinion was that the quantum electrodynamics project was an unmitigated disaster. The theory couldn't be solved. The equations had no sensible solutions. The mathematics had spiraled out of control. But Feynman believed that he could see a way through the mathematical complexity to a new truth. What Feynman did with all the arrogance and confidence of youth was slash through the insanely complicated maths. Feynman developed a new series of revolutionary but almost childlike diagrams to explain his new ideas. Their elegant simplicity flew in the face of the complex maths of traditional quantum mechanics. Conflict seemed inevitable. Then, in 1948, at the age of 30, Richard Feynman decided to unveil his controversial version of quantum electrodynamics with his idiosyncratic diagrams to the physics world. And he chose the most important science conference of the American calendar. Set on the coast of Pennsylvania, the Shelter Island Conference was a physics celebrity circus. Present were Niels Bohr, the so-called father of atomic physics,
the discoverer of antimatter, Paul Dirac, and the man behind America's atom bomb, Robert Oppenheimer. The atmosphere at the start of the conference was grim. Confidence in quantum electrodynamics was at rock bottom. It seemed a hopeless mess.
One after another, the physicists stood up and droned on despairingly about how they'd failed to find a solution. Then it was the turn of Richard Feynman. Barely 30 years old, he stood up and took his place in front of the world's most illustrious scientists and started to unveil his new diagrams and equations.
What happened next was astonishing. A row broke out, not so much over Feynman's weird description of reality. Physicists were used to weird by now, but because he dared to visualize what was going on. Instead of using arcane, complicated mathematics, Feynman was describing what all his virtual particles were up to using his simple pictures.
There was uproar. Niels Bohr, the father of quantum mechanics, leapt from his chair in disgust. He hated Feynman's diagrams because they went completely against everything he'd devoted his whole life to. You see, he believed that atomic particles could not be visualized under any circumstances. Feynman defended his new theory, trying to explain that the diagrams were simply a tool to help visualize his new equations. But the rest of the scientists, including Paul Dirac, wouldn't hear of it. They called him an idiot who understood nothing about quantum mechanics. Feynman ended his lecture bruised but unrepentant. He knew that his diagrams and equations were correct, if only he could convince the others. That evening, Feynman met another young physicist called Julian Schwinger. Now, Schwinger was the same age as Feynman and had been identified as a child prodigy at the age of 12. Although he and Feynman had been working independently and had approached the problem of quantum electrodynamics very differently, they'd reached identical conclusions.
With their new equations, they could solve quantum electrodynamics.
And with Feynman's diagrams, they produced a theory of awesome power. Together now as allies, they planned a full frontal attack on Niels Bohr and the conservatives. By the end of the conference, the mood in the Pennsylvanian roadhouse had changed from one of frustrated hopelessness to one of excitement and idealism. Over the next few years, their theory was fleshed out and rapidly became the most accurate and powerful theory mankind had ever had.
Despite finally being tamed, quantum electrodynamics' talk of empty space seething with energy we can't feel and virtual particles we can't see does make many people, including physicists, a little suspicious. And many skeptics might say these ghostly objects that allegedly fill the vacuum aren't actually real. Yes, the complicated mathematical equations of quantum electrodynamics seem to require them, but that doesn't itself mean they exist. They might just be mathematical fantasies with no basis in reality.
Well, I have bad news for the skeptics. Since the late 1950s, direct evidence that empty space isn't in the slightest bit empty, but is in fact seething with activity, has been observed time and time again in laboratories.
Quantum electrodynamics is by any measure a truly magnificent discovery. It's one great pinnacle of our story, a glorious conclusion to 5 amazing decades of science. In quantum electrodynamics, the atom had given us a theory that explains much of our universe with stunning accuracy. But since quantum electrodynamics' triumphant arrival in the late 40s, our story becomes rather messy and awkward. As a result of quantum electrodynamics, scientists were convinced that the vast majority of everything in the universe consisted of essentially just 2 things: atoms and light. light was made out of tiny particles called photons, and atoms were made out of three components: the electron, the proton, and the neutron. And because of antimatter, there were antiprotons, antineutrons, and positrons. A bit strange, but pleasingly symmetrical.
Everything in the physics garden was rosy, thanks to the rules of quantum electrodynamics. But then, much to the profound irritation of every working physicist, a load of new and exotic particles suddenly appeared like party gatecrashers to spoil the fun. Exotic entities that didn't fit into any known theories were appearing in physics labs with such frequency that scientists couldn't keep up with naming them all. The neutrino, the positive pion, the negative pion, the kaon, the lambda, the delta. And of course, each of these had their antimatter counterparts. When one new particle named the muon was discovered, one physicist quipped, "Who ordered that?" The whole thing was a mess that didn't make sense, and physicists despairingly referred to it as the particle zoo.
It began to seem as though every time scientists solved one of nature's mysteries, the atom would present them with something even more weird. Within just a few years, atomic physics had gone from a position of quiet confidence to total chaos. And of course, to make some sense of this new mystery would require, yes, you've guessed it, another scientific revolution.
The third genius in our story is Murray Gell-Mann. Gell-Mann was a child prodigy. By the age of 15, he'd already started at Yale to study physics and had finished his PhD by his early 20s. He had an incredible intelligence that terrified those around him. He spoke many languages and seemed to have this deep knowledge of any subject you care to throw at him. Like Richard Feynman, whom he joined here at Caltech in the early 60s, he seemed to have this ability to see beyond the mathematics and the formalism of his theories to the underlying secrets of nature below. Together, Gell-Mann and Feynman made an awesome duo. This office, number 456, used to belong to Feynman. But what's great is that just 2 doors along the corridor was the office of Murray Gell-Mann. There was an intense academic rivalry between these two intellectual giants, but they fed off each other's creativity. They were very different personalities. Feynman, who played the buffoon, Gell-Mann, the cultured elitist. Gell-Mann used to get upset by Feynman's loud voice, and Feynman certainly enjoyed winding him up. But it's fair to say that during the 1960s and 70s, these two geniuses here at Caltech dominated the world of particle physics.
Their bitter rivalry pushed them both to the very limits of their imaginations. And Gell-Mann especially was desperate to prove himself over Feynman by bringing some order into the particle zoo.
Within the feverishly intellectual atmosphere of Caltech, Gell-Mann's mind did something very strange. He started working with a different kind of mathematics to deal with the preponderance of subatomic particles. He used an obscure form of maths called group theory. As its name suggests, this is a theory that analyzes groups of numbers and symbols and tries to organize them into simple patterns and symmetries. It's a bit like working with an abstract form of origami. Using this technique, Gell-Mann started working all known particles into an organized system, which he called the Eightfold Way, after a Buddhist poem. But then he had his most awesome revelation. Gell-Mann realized that his group theory pointed to a new, deeper underlying mathematical truth, something which had the potential of rewriting the atomic rulebook.
What Gell-Mann's mathematics revealed to him was that in order to make coherent patterns of all the new particles in his eightfold way, he had to acknowledge that there was a deeper underlying fundamental reality. Once again, it turned out that things were not at all as they seemed.
You see, physicists have been comfortable with the notion that atoms are made up of 3 different kinds of particles. Electrons orbiting around the outside of a nucleus itself made up of protons and neutrons. Gell-Mann had the temerity to suggest that protons and neutrons were themselves composed of more elementary particles.
Particles that he called quarks. Murray Gell-Mann was cultured and arrogant, but at heart lacked confidence. He knew that for his colleagues, even those used to the strangeness of the atom, quarks were a step too far. And in any case, there'd been no evidence of anything remotely like a quark. He was convinced his new theory would be declared outlandish, or just wrong. So Gell-Mann sat on his revelation, and one of the greatest ideas in science was almost lost forever. Then something extraordinary turned up just a few hundred miles north of his office.
This is the Stanford Linear Accelerator, a few miles south of San Francisco. What you can see below me is one end of what is basically a giant electron gun. A beam of high-energy electrons is fired through a tunnel that starts off over 2 miles away in the hills. It travels underneath the freeway and comes out at this end where it enters the experimental area. The grey building over there is called End Station A and is where one of the most important discoveries in physics was made. It was built during the 1960s when it was, and still is today, the longest single building on Earth. And although it's 40 years old, you can see a lot of construction work is going on now. It's still being used for fundamental research today. I'm now inside the 2-mile-long linear accelerator building. The red objects you see on your right are called klystrons, and they provide the power that boosts the electron beam that runs 20 feet beneath us. Such is the acceleration, these electrons will, within the first few meters, have reached 99% the speed of light. Let me put it another way. If these electrons were to start off their journey at the same time that you fire a bullet from a gun, they would have covered the full 2-mile distance before the bullet has even left the barrel. The electron beam, now travelling at almost the speed of light, would have arrived here at the target area. There would have been in 1968, where I'm standing now, a large tank of hydrogen, basically protons. The electrons would smash into the protons and scatter off through tubes to be picked up by huge detectors that filled the hall outside.
And as they did this, physicists got their biggest ever confirmation that there might be a deeper set of rules underpinning the particle zoo.
What they had discovered, from the way the electrons scattered and because of their extremely high energy, was conclusive proof that protons have internal structure. In other words, protons were themselves made of more elementary particles.
Here were Gell-Mann's quarks. This was an astonishing moment. For decades, people were confident that the components of the atomic nucleus, the proton and neutron, were absolutely fundamental. And now, for the first time, there was evidence of something deeper.
The quark is a tricky and elusive beast. There are 6 different kinds or flavours of quark: up, down, strange, charm, top and bottom. Also, quarks never exist in isolation, only in combination with other quarks. This makes them impossible to see directly. We can only infer their presence. But despite these caveats, the quark brought some semblance of order to the particle zoo. In recent years, it's allowed us to concoct a simple yet powerful description of how the universe is built up. Basically, everything in the universe made of atoms is built up from just quarks and electrons. That's it.
This now brings us pretty well right up to date. The discovery of the quark in 1967 was the last significant experimental discovery of a new type of fundamental particle. Some say we may yet discover the quark is made of something even stranger, and it's possible. But for now, it's as good as it gets. Our journey from Einstein's proof of the existence of atoms in 1905 until now has been extraordinary. We've learnt so much about the atomic world, from the size and shape of the atom to how its centre holds the secret of the universe itself. From how it reveals an unknown world of antimatter to how empty space is far from empty. From what we thought was a basic building block of the universe itself to the discovery of something even more fundamental inside it. And yet, despite all the powerful science which we've uncovered, something doesn't quite add up. There are two startling and worrying anomalies. The first of these is now at the forefront of theoretical physics across the world, and it concerns one of the oldest scientific principles there is.
Gravity. Now, though gravity has been thoroughly understood since Einstein, it's never really been part of atomic theory until now. Suddenly, there's a glimmer of hope from ideas that sound almost too crazy to be possible. Some of these are called string theories that regard all subatomic particles as tiny vibrating strings that have higher dimensions of space trapped inside them. Some, called brane theories, suggest that our entire space and time is just a membrane floating through the multiverse. Another, called quantum loop gravity, suggests that nothing really exists at all, and that everything is ultimately made up of tiny loops in space and time themselves.
But despite gravity's unwillingness to fit in with quantum theory, I believe there's something worse lurking in the quantum shadows, something truly nightmarish.
Late into the night at physics conferences all over the world, over drinks at the bar, when we scientists huddle together to debate and discuss our strangest ideas and dreams, there are still things that really, really bother us. And chief among these are the quantum mechanical laws that atoms obey. And in particular, one aspect of these laws, something called the measurement problem. If you want to see fear in a quantum physicist's eyes, just mention the words, the measurement problem. The measurement problem is this: an atom only appears in a particular place if you measure it. In other words, an atom is spread out all over the place until a conscious observer decides to look at it. So the act of measurement or observation creates the entire universe. And just to show you how mad this idea is, I'm going to explain one of the most famous hypothetical experiments in the whole of science. It's called the Schrodinger's cat experiment. Erwin Schrodinger was one of the founding fathers of atomic theory, and in the mid-1930s devised a thought experiment purely to highlight the absurdity of quantum mechanics. He suggested you take a box in which you place an unopened container of cyanide connected to a radiation detector and some radioactive material. Now, the idea is that if an atom in the material emits a particle, this will be picked up by the detector, which in turn releases the cyanide. Next, you take Schrodinger's cat, which in this case is a lovely Norwegian forest cat called Dawkins. Now, I should point out that this isn't real cyanide. You place the cat in the box, you close the lid, and wait. So here's the conundrum.
According to traditional quantum mechanics, known as the Copenhagen interpretation,
All the time the box is closed, the radioactive atom inside has yet to make up its mind whether it has decayed and spat out a particle. So we have to describe it as both having decayed and not decayed at the same time. Think about what this means. Since the radioactive particle triggers the release of the poison, the cat is both poisoned and not poisoned. So until we open the lid to check up on the fate of the cat, what's called making a measurement, it's not just that we don't know, but that the cat is literally both dead and alive at the same time. This is clearly a paradox, or is it?
The paradox of Schrodinger's cat and the contradictory nature of the measurement problem really does force us to accept that tiny objects down at the atomic scale obey their own set of profoundly strange rules. But at larger scales, those of everyday human experience, those rules vanish, and an utterly new set of nice, intuitive rules take over. How can this be? Some argue that in fact the quantum weirdness of the atom might actually be writ large across the cosmos, that we may have to rethink everything we knew about the universe. In the last 100 years, we have peered deep inside the atom, the basic building block of the universe. And inside this tiny object, we have found a strange new world, governed by exotic laws that at times seem to defy reason.
Atoms present us with dizzying contradictions. They can behave both as particles or waves. They appear to be in more than one place at the same time. They force us to rethink what we mean by past and future, by cause and effect. And they tell us strange things about where the universe came from and where it's going. Pretty amazing stuff for something that's just a millionth of a millimeter across.
That's why Niels Bohr, the father of atomic physics, once said that when it comes to atoms, language can only be used as poetry.
What's fascinating to me is that although we've learnt an incredible amount about atoms and their behaviour, our scientific journey has only just begun. Because although we know how a single atom or just a few atoms behave, the way trillions of them come together in concert to create the world around us is still largely a mystery. To give you one dramatic example, the atoms that make up my body are identical to the atoms in the rocks, the trees, the air, even the stars. And yet they come together to create a conscious being who can ask the question, what is an atom? Explaining all that is surely the next great challenge in science.